Alright, welcome to lesson 16, Parametric Equations 2, where we're going to focus on the vector equation of a plane. And so the first thing that I want to do is drive home this concept of a plane and how we might move about one. And so we can think of this white screen as a plane, or just as the chalkboard in class is a flat surface, and that is also a plane, if it went on infinitely. Which some hours you may feel that way, right? So we look at this plane, we can draw hopefully a straighter line than that, an axis, a vertical axis like this, a horizontal axis out here, and so maybe we're going to label this X and Y. And so if we bring back the concept of standard basis vectors, you guys should remember that this vector I is equal to the vector 1, 0, 0. Draw that in right here. Right, and then we also have the standard basis vector J. So J was 0, 1, 0. That might look something like this. So if I wanted to put a point out there anywhere on this plane, I can put this point P. Right, so we'll call that point P over here. If I wanted to get to point P, I can use some combination of steps in the j direction or the I direction to get there, right? So some linear combination. So, if I'm allowed to move in the direction of I, then I'm also allowed to move in the opposite direction of I. So that's what I'm going to do here. So I've got to get out to here. So maybe this is one step in the I direction. We'll do another full step. And we'll go ahead and call that a third full step. So it took me 3 steps in the negative I direction. And then I got to start getting vertical here. Maybe that's 1, 2, 3, and okay, perfect. 4 full steps in the j direction. So I started at the origin, right? And then what I did was I moved 3i, actually negative 3 in the I direction, plus 4 in the j direction. And that got me to this point P, right? So that's how we move about planes. And now when we go back and we look at this theorem 2.5.1, maybe it'll make sense, right? And so I'm going to focus really on what's down here, but it says that this vector r of u and v, so those are the 2 parameters, is equal to r naught plus u times a plus v times b. And so if you think about it in the context of the problem we just did, this I vector, or a vector, is synonymous with the standard basis vector I, and the b vector is synonymous with the standard basis vector j, right? Those were the 2 directions that we were allowed to travel, okay? And then how we moved about this plane, this is how many steps did I take in that direction, I, or a, and this is how many steps did I take in the direction b, or in our example j, right? And then this r naught is the same as when we focused on, or when we introduced the vector equation of lines. It's just a starting point. It's a position vector to a point on the plane. And so in our example, that might have been the origin, right? So here's our definition. Hopefully now it makes a little bit more sense to us, because now what we're going to focus on is developing the equation of a plane given 3 points, and then testing to see if a point is on the plane. Alright, so here's our example that we're going to focus on. We've got 3 points, P0, P1, and P2, and given these 3 points, which are not on the same line, we want to find this vector equation of a plane. And so the first thing that we're going to do is I'm going to draw a little side sketch over here so that everyone understands what we have going on, right? We have 3 points in space, P0, P1, and P2, and we'll just put these points out here. What we're going to do is we're going to find, first it says let r naught be the position vector to P0, right? And so there's some position vector going out to P naught. And then it says we're going to let the direction vectors A and B be these displacement vectors. And so the first displacement vector is from P0 to P1, so we've got to find a displacement vector here and a displacement vector from P0 to P2, right? Okay, so that's the general concept of what we're going to do. So if R0 is the position vector of P0, that's easy. We can just say R0 is equal to this vector now, 4, 8, 3, right? Now we want to find A, so A is equal to this displacement vector of P0, P1, right? So to do this, we know that's equal to P1 minus P0, right? So we can rewrite these if we need to. So we can say 654 minus 483. That's going to be equal to 2, negative 3, and 1. Right, so that is A. And we're going to do the exact same thing for B. So B is equal to this displacement vector P0 to P2. So that's just equal to P2 minus P0, which is going to be equal to negative 1, 2, 2. Alright, so now we have all the aspects of this vector equation that we need. We know R0, we've got A, and we've got B. So now we're just going to substitute these vectors into our equation, and we'll have something that looks like this, where we say R of U and V is equal to our position vector R0, so 4, 8, 3, plus U times A, which was 2, negative 3, 1, plus V times our direction vector B, which was negative 1, 2, 2. Right, so given 3 points, we were able to formulate this equation of a plane. So now that we have this equation, the next thing we might want to do is solve to see if a point is on a plane. And so I've rewritten the equation of the plane right here. And we want to test to see if this point P is on the plane. So I've given you the point P is equal to 6, 8, and 19. And you'll notice that this point is written with parentheses because it's a point, not a vector, right? And so if this point is on the plane, then there should be some value of U and some value of V that would generate this point on the plane, right? So what we're going to do is we're going to set this point equal to the right-hand side of our equation. And if there's a U and a V that satisfy it, then we know we're on the plane. If there's not a combination of U and V that would get us there, then that means this point is not on the plane. And so here's what that'll look like. So now I've written the point equal to our expression, just to drive it home, right? This first term, that is our R0. And then we have U times our A vector and V times our B vector. And so if I want to simplify this expression, what I can do is I can subtract R0 from both sides. And so I'm going to subtract this vector right here. I'll subtract 4, 8, and 3 from both sides. And what that does is it leaves me with 2, 0, and 16 is equal to U times 2, negative 3, 1, plus V times negative 1, 2, and 2. And so I think it's worth highlighting that, you know, this first term in the vector, that corresponds to the x component of the vector. This second term corresponds to the y, and then the third term corresponds to z. And so if we wanted to rewrite this as a system of 3 equations, we could do that. And here's what it would look like so that we can solve this. So I'm going to switch back to black here, and we would say that 2 is equal to 2u, just doing scalar multiplication, and then minus v. 0 is equal to negative 3u plus 2v, and then 16 is equal to u plus 2v. So I've got a system of 3 equations with 2 unknowns, so I just need to pick any of the 2 equations I want to solve for u and v. So I'll solve 2, and then I'm going to check my solution here. Okay, and so I'm just going to tackle this first equation and simplify that. And so with just a little bit of manipulation, I can write that v is equal to 2u minus 2. Right, that was simple. And now we're going to solve through substitution, and we'll say 0 is equal to negative 3u plus 2, and here we substitute our v value in, 2u minus 2. So that says 0 is equal to negative 3u plus 4u minus 4. So 4 is equal to u. Alright, so I've solved for u. Now what I've got to do is I've got to take that answer and substitute it back in up here. And so when I do that, it's going to say that v is equal to 2 times 4 minus 2, which is equal to 8 minus 2, or 6. Right? So what I've found is u is equal to 4, v is equal to 6. And so we think we're home free, but we're not, right? We've got to check in that third equation. So my third equation said 16 has to equal u plus 2v. So we substitute our values in, and we see that it 4 plus 2 times 6 gives us 4 plus 12, which equals 16. So what this means is that point P is on the plane. Alright, so it was great that this point P was on the plane, but what are we going to do if the point is not on the plane? So that's the problem we'll take a look at next. And so I've already rewritten the problem up here. So we've got our vector equation of the plane. Now I've given you that this point P for negative 10, 3 is not on the plane. What I want you to do is I want you to find the nearest point, which we're going to call Q, on the plane to the point P. And so we've done a problem just like this yesterday where we were trying to find the nearest point to a line, and we found that what we had to do is we had to make sure that the displacement vector from the point to the line was orthogonal, right? Orthogonal to the direction vector. But now we've got 2 direction vectors. We've got this direction vector A and direction vector B. And so the shortest distance is going to be orthogonal to both of these. And so we're going to have to set up a system of 2 equations and then solve for the parameters u and v such that both equations are orthogonal. Okay, and so here's the formula we give you on the formula reference card for this problem. And so you may notice it looks fairly similar to the equation we used yesterday, solving for the closest point on the line. You know, this R naught plus UA plus VB, all that is a point on the plane, and that's the nearest point Q, right? So this whole expression right here is just a displacement vector, and we're making sure that our displacement vector from P to Q, when we dot it with the direction vector B, is orthogonal. And so we do that 2 times. So we repeat that up here as well, making sure that it's orthogonal to A. And so I'm going to go ahead and substitute all of our information into this problem, right? Because if we think about it, we know what R naught is, we know what A is, we know what B is, we know our point P, and we know B. So there's very little information that we have to find other than our parameter values for U and for V. Okay, and so I'm going to pause the video and write this out just because it takes a while. Okay, so I've gone ahead and I've written out all of our equations. Now I'm just going to zoom in here and label them one time for us. And so what I've got here is that's R naught plus U times A plus V times B this is minus p, now written as a position vector, dotted with a equals 0. And it's the same thing down here in red, except, obviously this direction vector that we're taking the dot product with is b. So I've left room just because now we're going to get into some algebra, right? And so all we're doing is we're distributing this dot product. And so I'm going to distribute this dot product A with R naught, and then I'll distribute it to this vector with U, and then with V, and then with P, right? So that's what we're going to do. I'm going to erase all these lines just so we have room to do some math. Okay, and so the first dot product I get in doing this, so I've got 4 times 2, so that's going to be 8. So I'm going to have 8 minus 24, and then plus 3, plus, now I've got 4 plus 9 plus 1, and all that has a u, plus, let's see, negative 2 plus negative 6 plus 2, all that is v, minus, and I've got 8 plus 30 plus 3, right? And so if I simplify this, I should have something that looks like, let's see, negative 13 plus 14u minus 6v and minus 41. And that all equals 0. And so now I'm going to simplify it one last time. I'm going to say that 14u minus 6v equals 54. Right? And now we're going to do the same thing down below. So we'll slide down here. We're going to do the exact same thing, distributing our dot product. And let's see what we get here. So I've got 4 times negative 1, so it's going to be minus 4. Minus 4 plus 16 plus 6. And then I've got, let's see here, negative 2 minus 6 plus 2, and that's u, plus, let's see, 1 plus 4 plus 4, v, and then minus, what we have here, we've got negative 4 minus 20 plus 6, right? And all of that, again, equals 0. So we are going to go ahead and consolidate here, and I've got 18 plus, what is that, minus 6v, or minus 6u rather, plus 9v, minus, so that's going to be negative 18, so plus 18 equals 0. And so we'll go ahead and simplify this one final time and just rewrite it so it says negative 6u plus 9v equals negative 36. Alright, so here's my 2 equations that I've got to use, right? So I've got this equation and this equation. And so I've got to solve this system of equations now. So I'm going to rewrite them over here. Just give me a little bit of room to work, right? And so I've got 14u minus 6v equals 54, and then I've got negative 6u plus 9v equals negative 36. And so just to solve this system of equations, showing you a different method than substitution, we'll use the method of elimination. So with the method of elimination, what I can do is I can multiply this top row by 1.5 and rewrite it. So if I do this operation, it's going to give me 21u minus 9v equals 81. And now what I'm going to do is I'm going to add that to this bottom equation down here, and we get 15u plus 0v is equal to 45. Now I can solve this expression for u. So 15u is equal to 45, or u is equal to 3. So if u is equal to 3, now we just substitute that back into either one of the equations. And so I can do that and say we'll use the bottom equation down here. Switch back to black and I'll say negative 6 times 3 plus 9v equals negative 36. So that's negative 18 plus 9v is equal to negative 36. Add 18 to both sides. 9v is equal to negative 18, so v is equal to negative 2. And so there's my answer for u and for v, right? But I still don't know the point q, and I won't know it until I substitute these two values into the equation of the plane. Right? So I'm going to take these two values that I just found right here, and I'm going to substitute them in up here for u and v. And so I'm just going to rewrite these right above. Actually, I'll just go ahead and erase these. So u we now know is 3, and v we now know is negative 2. And so we can distribute these values. I'm going to do that right off to the side. And we'll get something that looks like this. So I'm just going to draw an arrow over here. We've got this vector 4, 8, 3 plus 3 times the vector 2, negative 3, 1 plus negative 2 times our vector negative 1, 2, and 2. And so if we distribute these values, we're going to get the vector 6, negative 9, and 3, plus this vector over here, which is going to be 2 minus 4 minus 4. Let's not forget our not. 4, 8, and 3. So now we're just going to add up all of our components here, right? And so we get this point q, which is going to be equal to, let's see, we've got 4 plus 6 plus 2, so that makes that 12. 8 minus 9 minus 4, so it's minus 13. 8 should be minus 5. And then 3 plus 3 minus 4, so that should give us 2. So if all my math works out, here's our point Q, and that's the closest point on the plane to the point P.